Welcome to the BKR chemistry classes. Today we are going to see NMR spectroscopy and I'm going to focus on two NMR active nuclei, proton and C13 carbon. As I have mentioned here, NMR active nuclei. So for a nuclei to be NMR active, it should respond to an external magnetic field. That is very important. So in order to respond to external magnetic field, it should have magnetic moment. And this magnetic moment depends upon the spin quantum number I. So as we can see in this particular picture, so a nuclei which has charge and which is spinning. So any spinning charged nuclei will generate a magnetic moment nu, and this nu is proportional to gamma, and this nu is also proportional to the spin quantum number. So a nuclei which has spin quantum number I not equal to 0 will generate a magnetic moment and it will be NMR active. So in other words, I can say a spinning charged nuclei will generate a magnetic moment and such nuclei will be NMR active. So we have given here example proton, carbon, fluorine, phosphorus. So, a spinning charged nuclei will generate a magnetic moment and they'll behave like a little magnets. And when you put them into an external field P0, they will respond to the external field. So, now the next question is what are the nuclei which will be having I not equal to 0? So let us see that. So any nuclei which has number of protons and number of neutrons even, both are even, that will have I equal to 0 and they'll be NMR inactive. Very simple to remember. Other than that, if any one of them is odd, number of protons or number of neutrons, any one of them are odd, then they will be NMR active. They all will be NMR. So all these are NMR active because they have either the proton or the neutron odd. So they'll be NMR active. Now in this you can have a clue. So if the number of protons and number of neutrons is equal to odd, so number of protons and number of neutron is equal to odd, you'll be having the I value a integer, the whole integer. It will be 1. Suppose you have either the proton or the neutron which is even. So either the proton or the neutron is even, then you'll be having the half integral. You'll be having the half integral. So keep that in mind. We are going to focus only on carbon and hydrogen. As you can see, they have I value equal to half. So when I have I value equal to half, when I put them into an external magnetic field, B0, they'll be split into 2i plus 1 state. 2i plus 1 state. So it will be equal to 2 states. So they'll be split into 2 states. Here I'll be having plus half state. So I say z equal to plus half and z equal to minus half state. Something known as Zeeman splitting. So when I is equal to half, the splitting will be only into 2 states. So it becomes very simple for me. So when I give a radio frequency mu 0, I'll be having the excitement from the lower state to the higher state. That's all. It becomes very simple. But if I have more than one states, I'll be having multiple number of excitation, multiple number of relaxation. That makes the spectrum very complex. So I'll be sticking on only to I equal to half. So basically, you can have very easy spectrum for proton, fluorine, phosphorus, and carbon. It is very easy to study them because the spectrum will be very simple. Next, now when I put them into an external magnetic field, what happens? There will be not only the splitting of states, the nuclei will also precess. So it is like the precision of a top. You can see here I put a top picture. So you know that top undergoes rotation and revolution. Okay, like Earth revolves around the sun. So Earth undergoes rotation and revolution. Similarly, here you can see this will be spinning around itself and it will be also spinning around the axis. Okay, so this spinning around the axis, so this orbit is known as precessional orbit, and the precession number of radians per second is known as precessional frequency omega 0, and this omega is equal to gamma into b0. So omega is the precessional frequency. It's also known as the Larmar precisional frequency, and it is equal to gamma into B0. That is the gyromantic ratio and the magnetic field, external magnetic field. Gamma is the ratio of magnetic momentum by angular momentum, and this values are listed so that I'll show it to you. So you can easily pick the values of different nuclei from the table. Now you can see that this special frequency is directly proportional to this gamma, and it is also proportional to the external magnetic field. This is very important to know. So when I put a nuclei into external magnetic field, it not only undergoes splitting, it also undergoes precision. And the precision frequency is known as omega zero, or which is known as Lama precision frequency, which is equal to gamma B into zero. Now, how are they related to the energy difference? So this is a splitting energy. So the splitting between the levels. This is delta E. Now this delta E is equal to H gamma B0 by 2 pi, or I can say H omega 0 by 2 pi. And this energy is also equal to the H nu, which is the radio frequency which I'm going to support or give to excite the nuclei from the lower state to the higher state. So now we can see that nu is equal to omega 0 by 2 pi. Very important equation. So mu is equal to omega 0 by 2 by substituting for omega 0, we know that omega 0 is gamma into b0. We get that mu is equal to gamma b0 by 2 pi. So this is b0 is the strength of the applied field, and mu is the frequency of the incoming radiation that will cause a transition, and gamma is the gyromantic ratio. So when this mu proportionates the omega 0, what will happen? I'll be having the excitation from lower level to the higher level, and this is known as resonance. So when this radio frequency resonates with the precisional frequency, the nuclei will get excited from the lower state to the excited state. That is why it is known as nuclear magnetic resonance. Is it clear? I hope. Okay. Now let us see simple problems. So the first problem is the spin motion of which of the following nuclei will have magnetic moment. So as I had mentioned already, then for a magnetic moment you should have a spinning charged nuclei. So based on that you will immediately answer it as A and B, but the answer is option 4. The reason being neutrons actually they don't have any charge. So what we will feel is since neutrons do not have charge, they will not have any magnetic moment. But neutrons are made up of three magnetic quarks, and the magnetic quarks have magnetic moments. Those magnetic moments sum up to give neutrons its specific magnetic moment. So, in general, electron, proton, neutron, all the three have the magnetic moment. So, the answer is option 4, A, B, and C. So, just you can Google for magnetic quarks and get to know more in detail. Now, this is June 2023 question, very recent question. They have asked for NMR inactive nucleus. See how a simple question they have asked. And what did I say already? You just check the number of neutrons and number of protons. If both are even. Both are even. Okay. If both are even, then I will be equal to 0. And if I is equal to 0, mu will be equal to 0. And they will not respond to an external magnetic field. Therefore, they will be NMR inactive. So for I equal to 0, even, even. So you can see, you can easily pick the answer. Option 3 is the answer. So either the number of proton or the number of neutron should be odd in order to have NMR active nuclei. Very simple question, is it not? This is a very recent question, December 2023. They have given the gyromantic ratio of the proton, which is 26.752 in 10 power 7 radian Tesla inverse seconds, and the magnetic field, which is 21.1 Tesla. They're asking for the Lama frequency for the proton. So we know that Lama frequency is equal to omega 0, which is equal to gamma into B0. Just substitute and find the answer. They have asked for approximate answer. It comes around 600. Next question. The proton NMR frequency at 1 Tesla is 42.4. The gyromantic ratio of proton and carbon are 27 and 6.75 10 per 7. What will be the C13 frequency at 1 Tesla? We know that the frequency is equal to gamma B0 by 2 pi. So on substituting, suppose I have frequency of carbon will be equal to gamma of carbon. I'm dividing by the frequency of hydrogen. So it will be divided by gamma of hydrogen because the magnetic field is remaining constant. They're asking for the frequency at 1 Tesla. So B0 will get cancelled. So I'll be having frequency of carbon by proton will be galvanic ratio of carbon by proton. Okay. And now we have to just do the substitution. So frequency of carbon will be equal to galvanic ratio of carbon, which is 6.75 into 10 power 7 into the frequency of proton, which is 42.4, divided by the gamma of hydrogen, which is 27 into 10 power 7. So this is approximately 4 times. So the answer is 10.6. 10.6. I need not do all these calculation. If proton frequency is given and they're asking for carbon frequency, just divide the frequency of proton by 4. Finished. Because the gyromantic ratio of carbon is 1 by 4 the gyromantic ratio of proton. So if proton frequency is given and they're asking for the carbon frequency, just divide the frequency of proton by 4. So 42.4 divided by 4. Finish. Within seconds you can answer this. No need of doing all such things. So I've done all this just to make it sure that if you just forget this 1 by 4, all that stuff, you can easily substitute and find the answer. Okay, but very simple. Proton given, asked for carbon, divide by 4. Okay. What else can be done? So you can see that the proton is 26.7 10 power 7. So it's 2.6 they have given. So 26.7 10 power 7 and carbon is 6.7. So the ratio is 1 by 4. When I compare the proton and nitrogen is 1 by 14. So if proton is given and they're asking for nitrogen, what will you do? You will divide the proton frequency by 14. Finish. Very simple. Don't do anything else. Just the proton frequency divided by 14. Okay, if I ask a question, if proton is given and they're asking for fluorine, what will you do? They given proton, they're asking for fluorine. What will you do? How are they related? We can see for proton it is 2.6 into 10 power 8 and for fluorine it's 2.5 into 10 power 8. They're almost same. So if proton is given and they're asking for fluorine, just write the same value. Approximately, they'll put the word approximately. So proton and fluorine will be having approximately the same frequency because they are very close. They just differ in the first decimal, zero point 0.6, zero point 0.5. Okay, so it becomes very simple. So if proton is given and carbon is asked, divide the value of proton by 4, divide by 4. If proton is given and they are asking for the value for nitrogen, divide by 14. Okay, if they are asking for fluorine, divide by nothing, divide by 1, nothing. So it will be same. Suppose vice versa, they're giving the value for carbon and they're asking for proton. So multiply by 4. Okay, so this you are sure enough to answer in such way. Okay. So now look at this question, June 2015 question. They are given the G factors of proton and nitrogen 5.6, 0.40. Now, if the magnetic field in the NMR spectrometer is set such that the proton resonates at 700 megahertz, the 14 N nucleus, this nitrogen 14 will resonate at, as I told, so 700 divided by 14. Finish. Very simple. It is 50 megahertz. Answer is 50 megahertz. Finished. See how easily we are able to solve these.